In my talk today, I will talk about data quality assessment, image artifact correction steps, and a bit about the methodological considerations when processing and analyzing your diffusion data. And I will start with the data quality assessment in a typical way as I go through my work. So I'm in the office, and this is me. Okay, so this is the nerdy physicist doing some processing, methods development. And then the lovely, charming, very smart Dr. Kate steps into my office. And you can already see she's got the heart in the right place. And then she basically asked me like, hey Alex, I've been collecting some advanced DTI data. Can you help me with the analysis? And then obviously I'm very happy that she enters my office and I start dreaming about the high quality diffusion data. But in practice, I get very sad, okay? Because then she turns up to me with some data. She says like, this is my data. And then I'm like, And she's like, well, but I've collected 300 of them. So, it's kind of problematic there. And the point I want to make is that in a typical pipeline, a very lengthy pipeline of diffusion MR analysis, it's this step which is typically neglected, right? So people acquire the diffusion data and start modeling and number crunching away, and they're very happy they can work with their data. But if you look at this example, so these are 18 different data sets from different centers across the world. You can appreciate the diversity in data quality, right? If you look at this, for instance, is this a monkey brain or what is this? I mean, you can hardly identify that this is a human brain. So it's very diverse, and I just want to focus on a few examples to see what went wrong with this data. Okay, so let's focus on this one. In this case, if you're a novice to the field, you think like, nice colors, but if you're more experienced, you can clearly see some fishy things going on here in the gene of the corpus callosum, especially the blue patch here. Well, in this case, the subject was not informed to lie still in the scanner. And obviously that's problematic with MRI, so you can clearly see that the subject is moving around. Okay, so this is just a quick and dirty trick if you want to just look at your data. You just need to look at your data and get a feel of what some artifacts, or in this case subject motion, would induce on your data. It still looks like a relatively normal data set, but you can clearly see it was not properly processed in this case. Another example is to look at your data from different viewpoints. Okay, so we typically acquire our data axially, but if you look at your data from a sagittal or coronal point of view, you can easily spot artifacts. And you can clearly see this signal dropout over here. That's perhaps less, interesting. But did you also notice this kind of hyper-intense band of signal over here, which kind of fades off towards the other side? Well, this is something you would never spot by just looking at your data axially. Okay. So again, if this is a one-off, I wouldn't worry about it too much. But this was a systematic artifact which was present in all the data sets and at different levels across the brain for different subjects. Okay, so this is definitely going to complicate your interpretation of your outcome. Let's look at another example over here. You notice anything interesting, artifact-ish? Well, in this case, the typical color convention was not really, adhered to. In this case, the front-to-back orientation is in blue, right? Look at the association pathways over here and over here, and in green, the corticospinal tract. Is this wrong? Well, if you're really strict, it's not wrong, it's just a convention, right? So as long as your coordinate systems are matched up nicely, it's fine. But this is what we would use normally, right? So if you compare, this is the unconventional, this is the conventional color encoding. What can be problematic, obviously, and this typically happens when you play around with different software packages, exporting your diffusion data from one package to another, then there might be coordinate mismatch issues like flipping of signs, etc. Okay, so in this case, you would say that this is a nice data set, and if you look at this coronal view of the corpus callosum here, you can see that the orientations are nicely aligned with the underlying orientation of the tissue structure. But in this case, the coloring stays the same, but clearly the orientations are now flipped. Okay, so this is wrong. Well, this is obviously problematic if you then start to do tractography, because on the left-hand side, you get a result which looks like this. It's the same data, but then correctly processed, you get something like this. So be careful when Dr. Kate says like, we should publish this to Science. Look, this subject doesn't have a singulum bundle. Well, you may want to check, was there a simple flip sign issue here, okay? Okay, another one. This is also interesting, especially again if you're new to the field and you see all these colors, but there's a clear artifact. And again, If you're more experienced, you probably see that in the back of the brain, this red patch over here, very bright means there's a coherent structure, red means left, right. So we have a coherent bundle going from the left to the right occipital pole. Well, it's very unlikely, right, that we have these direct connections. So you may want to look into this, like, how do I know which color is correct, and, is there any quality assessment here? Well, we need to, or we can resort to something what is called the residuals from your model estimation. So I just make a kind of analogy here. So if you have a set of points and you fit your line, this is your model if you want, then the residuals are basically the differences between what you measure, the yellow dots, and the predicted values, the estimates, in this case derived from your red line. Okay, so these are the residuals. Well, with diffusion MRI, we can do exactly the same. If you have a model, let's say the diffusion tensor model, we can fit the model to the data, then put it back in the equation and predict what the diffusion weighted signal should have been given the diffusion tensor. And then we can do exactly the same. We can subtract both from each other, and then we basically take the absolute value, average across all the diffusion weighted orientations, and you'll get a map like this. Okay, so kind of the kind of rule of thumb is that these should be uniformly distributed, so there shouldn't be any structure in there. So it's basically just the noise, what remains, and these values should ideally be low. Okay, so in this case, I would argue, well, it's a good quality data set. You may argue, well, it's a bit noisy, indeed, but at least there's no systematic artifact in there. So looking back at this example, there you go. That's the residual map. So you can clearly see the region highlighted over here that we've got high residuals, meaning there's a big difference between what you predict and what you actually measure. Luckily, this kind of artifact is called, this is a vibration artifact, and luckily it can be mitigated by this tool developed by Carla Miller, so how to address this systematic vibration artifact. Another example, and this is a bit more challenging. So to spot this artifact, you can't even do this on the color-encoded FA map anymore. But if you look at the residual map, you can clearly see this kind of region. It's intense region. There was insufficient fat suppression, and you can clearly see this artifact. And maybe going back, you could argue, well, it's a bit dark over here. Well, this increased variant causes a bias in your estimate, and then you might see it. But it's really difficult. Okay. And finally, here's an example, again showing the residual map as well. Well, in this case, there's actually no artifact. So you may wonder, like, okay, what's going on over here in these regions? Well, there's always a flip side to the coin in terms of residuals. On the one hand, we've got our data, what we acquired, and we've got our model. But what if the model is not correct given the data? Okay, so in this case, for instance, a line would be a good model in my view, and a sinusoid would be a bad model. In this case, my residuals would be higher compared to the linear model here, right? So the same holds actually for this example. In this case, the data was acquired, on a very, in a very good neuroimaging center, data quality was assessed, etc., etc. But in this case, the B value was 3,000 instead of the more typical 1,000. So instead of looking at the hindered diffusion regime, one would be looking at the restricted diffusion regime. So in this case, our model was not appropriate, especially in regions where you have these kind of crossing fibers, and I'll come back to that later. Okay, and this is an example that can be actually, kind of drives this point home, is that if you look at this example over here, this is high quality data. As you can see, it was actually acquired by a team of Russ Poldrack, so it's about myconnectome, you may have heard of this. And basically, this, Russ scanned his brain for, I think, more than a year, a lot of data. And then at some point he asked me to analyze his diffusion data. So I looked at his data, and indeed in this region, something funny popped up, right? So I was like, okay, Russ, are you aware that you've got a special brain? I mean, we all know he's very smart, so he must have a special brain. But in this case, it was like, what's going on here? Is this an artifact? And this is where residuals come to the rescue. If you look at the residual map, it looks fairly homogeneous. And I was like, okay, this is genuine. So there's a genuine microstructural abnormality in Russ's brain. Okay, it's published, it's out there, his data is available, you can look at his brain if you want. But interestingly, this kind of hyperplasticity or whatever you want to call it, it's actually more common than you think in the corpus callosum. And recently, I think the Oxford group and some others have actually shown that this dispersion in the corpus callosum is very prominent. But this is an extreme case, I would argue, because here the dominant diffusion orientation is actually front to back in green, compared to the left-right from the corpus callosum, what you would expect. Okay? But again, I want to focus here on the residual map. It's very convenient to kind of disambiguate, like, okay, what am I actually looking at? Okay, another one. If I look at this one, you know, anything abnormal, it's really difficult to see. And the artifact here is related to what I would call physically implausible signals. In short, this. It's probably not really a very diplomatic acronym, and especially in the States, using this for journals, they didn't really like it. But anyway, we got it pushed through. What I mean with PIS is anything in our data which we don't expect. And if you look at our diffusion signal over here, well, we know that e to the minus something positive should always be smaller than 1, meaning that our diffusion weighted signal is always lower than the non-diffusion weighted signal. This is what we expect, right? This is the entire principle of our diffusion attenuation. But in practice, we notice that there's many regions where the signal is actually larger. The diffusion weighted signal is larger. Okay? So this is artifactual. This is physically non-plausible. And if we look back at this example over here, in the splenium of the corpus callosum, there's many regions that show this kind of PIS. Okay? So I'm just overlaying in red any region where there's a diffusion weighted signal which is larger than the non-diffusion weighted signal. So this is unexpected. So obviously, as a, you know, through Sherlock Holmes, you start investigating, like, why is this? And you go all the way back to the raw data. And in this case, if we focus on these 4 voxels over here and look at the corresponding non-diffusion weighted map, well, you can appreciate that these signal intensities are very low. You know, they're artificially low. But why would that happen? Well, in this case, the artifact is referred to this guy. This is Mr. Gibbs. Okay, so we've got Gibbs ringing, and this is a very common, well-known issue in MRI. If we haven't got enough high-frequency content, we cannot, you know, basically describe or characterize the sharp transitions from high signal to low signal. Okay, so in this case, you could make the analogy like our CSF signal, the very bright signal, is over here. This is the lower signal of the corpus callosum, and just at the edge, you get this undershoot. Okay, and this is what you see, for instance, near the ventricles. So if you focus on this B0 image over here, you've got very bright signal in the ventricles, and then you've got this kind of very low signal, the undershoot, and then you've got the normal signal, what you would expect in white matter. Okay, and then if you indeed look at the color-encoded FA map, you wouldn't really notice anything abnormal, but then if you overlay this PIS map on the FA, you can clearly see, like, in these regions, you see something funny going on. And typically, you see an overestimation of the FA, which can be pretty large, you know, even 50% or more. So here's another example, higher up in the cortex. So we've got a subject with some atrophy here, so an older subject, a lot of CSF, and then you can clearly see this Gibbs ringing going on and all these artifactual estimates of the diffusion properties. Can we do something about it? Yes, there's many techniques available nowadays, one of which is a total variation approach, kind of off the shelf. And here I'm going to show you before and after correction. So if you were to naively just reconstruct your diffusion properties, you'll get something like this. And focus, for instance, on the edges over here or near the splenium of the corpus callosum. So this is before correction, this is after. Okay, if I toggle between them, you can clearly appreciate that the hyper-intense overestimations get mitigated over here. Okay, and also notice that the sharp transitions, the edges, they're not blurred out. So you could have used an isotropic Gaussian smoothing approach. It's also quite common, but that obviously has a disadvantage to blur out your edge information. Okay, now I'm going to go through a few image artifact correction steps. And the first one is related to signal intensity drift. So if we acquire our diffusion data, typically nowadays we acquire also multiple B0 images. And if you were to do this in an interleaved fashion, you can clearly see that in this case, well, you've got some signal decrease over here. Okay, so if you just take the average intensity value of your B0 image, you can clearly see that over time, the signal goes down. And that basically just says, like, okay, your scanner is not perfect. You know, it might be heating of the system, or, you know, depending on how many times you used your scanner or whatever, you get different trends over here. And this is, I guess, very common in fMRI. People have been correcting for these kind of signal drifts for many years, but in diffusion MRI typically has been neglected. Also because obviously if you look at the diffusion weighted contrast, and here the three different rows over here, they represent three different B values. So you've got B value 1000, 2000, and 3000. You can appreciate, maybe you can still observe the kind of trend over here, so it's also decreasing, but with the other B values it's really difficult. And in addition, it's the contrast in the diffusion weighted signal itself depends on the orientation, right? So this drift is really difficult to spot on the diffusion weighted signals themselves. Luckily, you can correct for this in an almost trivial way, because if you've got these multiple B0 images over here, you can just fit a low order polynomial to it, and then use that trend information across all your data and correct for it. And some people argue, well, I only have one B0 image. Can I still correct for the signal drift? Yes, you can, as long as your B value is, let's say, not more than 1500, because then this trend cannot be reliably estimated anymore. Okay? And this is something which is nice in a way that even if your data is perfect, you can still use this correction tool, because then it would be a unity operation, right? If you have just a constant, basically, you wouldn't change your data. And also it takes only 1.5 seconds to compute on a 60 direction data set, so that's convenient as well. And this is just an example before and after correcting. So I'll just quickly toggle, and I hope you can see the global intensity difference. So it's a very global one, and in addition, it's also non-uniform. So if I just take the absolute value of the FA, for instance, you can clearly see there's structure in there, right? So different regions will exhibit a different bias because of the signal drift. And also, obviously, the absolute FA difference doesn't mean a lot. If we take it percentage-wise, then notice that the vast majority of differences before and after correction can go up to 2%. All this area over here is definitely more than what you expect from a typical effect size when comparing different populations, for instance. So this will clearly help, at least in the sensitivity to find your statistical results there. Okay, another one is related to subject motion. Well, this is our subject again that was not informed to lie still, so you get these kind of dodgy estimates of your diffusion data, and if you then apply a correction, like in fMRI, typically use registration, and then now they're all aligned. One big difference, however, with fMRI is that our contrast is actually orientation dependent. So if you correct for subject motion, you should also correct for the applied gradient information, right? So here's a toy example that kind of exemplifies this. If you have a subject rotated like this, and let's say this is a fiber pathway, if you were to just naively use spatial registration, then you'll get this, okay? And you can appreciate that at each location in your data set, the orientation should also be corrected, okay? So this is what we call without the B matrix rotation, and then if you apply this B matrix rotation, then it's what you should expect here. So here's an example. So if we look at our diffusion weighted volume over here, and then you apply a diffusion gradient weighting in a specific orientation, just think of this of this blue 2 billiard ball here in a specific orientation. If our subject now moved, okay, there you go, got subject rotation, then you apply your diffusion gradient, you get something like this. So if you then were to naively use registration like in fMRI, you can appreciate that the contrast is now different. So if you were to estimate your diffusion properties, you'll get something like this, and here you can clearly see some dodgy estimates in your splenum of the corpus callosum. So the blue ball over here, what you need to do is basically, if you reorient over here, just reorient the gradient orientations. Okay, it's that simple. And simultaneously, we tend to correct for eddy currents. So in the previous talk, Jennifer also mentioned that you've got these fast switching gradients causing these artifacts in the data. Well, you'll still tend to have some residual misalignments there. If you don't correct for them, or if you correct for them not in a proper way, you can still see these kind of bright edges here. And if you correct for them, they will get rid of them. But it's not just the edges, right? So if you focus on the middle parts of the brain, you can also clearly see the improvements. Another artifact is related to EPI deformations. So in this case, if I were to just rigidly align my diffusion data with, let's say, an artifact-free in terms of geometry, fidelity in a T1 weighted image, then you can clearly see here that in the front of the brain there's a stretch, while the back of the brain seems to be nicely matching. Okay, if I just use the edge information from the diffusion, you can appreciate that you've got a nice alignment in the back, but here in the front things tend to be stretched here, okay, due to these susceptibility artifacts. So I'm just going to show you a few examples before and after correction. So again, if I use rigid alignment between the two data, you can clearly see the geometrical misalignments over here, and this is after correction, so before, after. It's not perfect, but at least it's doing a better job than not correcting for this. And this is obviously an area notorious for these artifacts, the orbital frontal cortex. And then some people argue, well, higher up in the cortex, the regions there where I'm interested in, I don't see these artifacts. Well, again, if you were to rigidly align them, you may debate, well, is this a good alignment? Well, again, this is before, this is after. And I would argue that after correction, it looks better. And you can see shifts up to 2 voxels, which obviously from a T1 point of view, 2 millimeter, for instance, is significant. Okay. And some people then say, like, okay, but what's the trick? Because if you're doing this high nonlinear registration deformation model to warp these data, it can go all over the place, right? These optimization procedures are very sensitive to, for instance, initialization, etc. But the nice thing here is that we actually can constrain our degrees of freedom to the face encode orientation, right? These distortions are dominant in the front to back orientation. So in this case, I'm showing you a sagittal view, where if I just show you before and after, you can clearly see that indeed these artifacts are just front to back. Okay, they're highly nonlinear. Focus on this area, clearly see it's going to the back, and here it's going to the front. Okay, but at least you can constrain it. So you don't need to optimize, up-down orientation here, because there's no artifacts going up-down, or at least not significant. And interestingly, if you change the face encode, or the polarity of the face encoding, you can still see differences in your final outcome. Okay, so even after correction, you can still see, observe these differences in your general question, so in the final outcome of your analysis. And obviously, if you do have phase encode data acquired APPA, then I would recommend using the FSL tool here to combine everything and get rid of the artifacts here. And finally, on the pre-processing steps, it's the estimation. So there's many ways to estimate your diffusivity properties. You've probably heard of the ordinary linearly squared, weighted linearly squared, non-linearly squared, conditionally linearly squared, and et cetera, et cetera. There's many ways to estimate your diffusion parameters from your data. One thing, obviously, is that if you have artifacts that typically shows in the form of an outlier, is that what you should do is use robust approaches. And for any statistician, it's trivial, but in a diffusion setting, typically people have not been doing this in the past because of computation issues, right? It takes a long time to compute in a robust fashion. Okay, so what you should do, or at least, so what happens, obviously, if you have an outlier, then your estimates will be biased towards the corrupt data. So what you should do is identify the outlier, get rid of it, and then estimate your diffusivity properties with the remaining data points. Here's such an example. So this is what the scanner console provided us, because they don't have the robust estimates implemented. So this was a child with a lesion moving a lot. You get this kind of dodgy data. This is after using a robust approach. In this case, it was the rekindle approach developed by Chantal Tax. Okay, and finally, a few methodological considerations I want to add. So there's many ways to analyze your data, and it's a blessing, but sometimes it's a nightmare because we need to make decisions. Like, what approach are we going to use? And it depends highly on your research question, right? If you're not interested about specificity in terms of location in the brain, well, you may want to resort to a histogram analysis, kind of 1980s, but it still works. It's useful. There's many ways to do this, right? So many approaches to analyze your data. And one of the most popular ones, arguably, is fiber tractography, but that's not perfect either, right? And in the coming talks, you will be, hearing a lot more about assumptions and models, etc. But what I want you to be aware of is that what we do with tractography, and while it looks like we're reconstructing fiber pathways here, it's not a direct measure of these pathways, right? So these are not axons, right? These tubes, they do not represent the thickness of the axons in any way. Okay, we're just conveying here the kind of architectural configuration, something connecting orbitofrontal to temporal region. Well, it must be related to the uncertain fasciculus. But it's not perfect, right? And you should be aware of this. Especially if you think of the data itself, right? The data is noisy. So instead of showing you this kind of nice color-encoded lines, I could have shown you something like this. So this is what I would call the trumpeting brain. You may have seen this before. In this case, what I'm just showing you is the uncertainty associated to each point along each pathway in the brain. So you can appreciate that some regions, you can have more, let's say, certainty in that it's a genuine pathway in terms of precision estimates. But some areas you may want to be very careful in terms of saying like, it's definitely going that way. Obviously, if you show this to a medical doctor, they'll freak out. Okay, so don't do this. It's more like a kind of a conceptual idea that these data they are not perfect. Okay. Another aspect is related to partial volume effect, and in this case, I'm just going to quickly show you the effect of having two different sizes of a bundle. So if this is my fiber bundle, kind of approximated with a cylinder, then if you have a small fiber bundle, a thin one, then the effect of the partial volume affected voxels at the edge will contribute more to the final estimate than a thicker fiber bundle. Okay, it's kind of roughly a 1/r, with r being the diameter here, or radius. So it's a dependency that suggests that if you have bigger tracts, the estimates of the diffusivity properties, like DFA, will be higher compared to thinner tracts. So we just put it to the test. So here's a part of the limbic system here, so single bundle, and we use our virtual scissors. We cut them open, look at the cross-section, and then estimate a kind of rough diameter approximation of this cross-section, and then correlate it with the FA. So in this case, visually, you can already appreciate that in the middle part, you have high FA estimates, and at the edge, due to partial voluming with gray matter or CSF, these values are lower. And if you then indeed do the association, it's kind of amazing to see that the vast majority of the variance in your FA estimates can be purely, predicted, if you want, or explained, I should say, by these thicknesses of these pathways. Okay, so in this case, I just want to emphasize that if you're comparing, let's say, different groups, check whether some morphological aspects like volume are actually driving the difference here. Okay, and luckily it's not the only aspect here. So if you take, for instance, volume as a confound not of interest in your analysis, you can still come up with, obviously proper estimates of your microstructural organization in that area. And another one I will briefly touch upon is related to the model assumption of the DTI. So obviously, with DTI, we assume that we've got Gaussian diffusion, right? We've got, let's say, unifiber populations where these molecules are spreading around in a Gaussian fashion. But in practice, obviously, we have these complex fiber organizations, at least at the scale of a voxel size, right? So kissing, branching, crossing, bending, whatever you want to call them. Typically, we call it crossing fibers. There's, it's genuinely there in a 2 millimeter resolution. And if you don't believe me, here's a polarized light imaging microscopy image. So this is near the medulla oblongata, so just below the brainstem. Okay, obviously this is ex vivo. Okay, otherwise diffusion MRI would be out of business, because this is a resolution which is extremely high, right? If I overlay our diffusion resolution, we'll get something like this. Okay, so this is our typical 2 by 2 by 2 voxel size, and you can appreciate the heterogeneity of all these orientations here, right? So indeed, people saying like, let's just acquire data with some higher resolution and we'll get rid of these crossing fibers. Well, that's not going to happen. Okay, even axons branch. Okay, and this is at the micrometer level. So what can we do about these crossing fibers? Well, a lot. Okay, this is not even an exhaustive list, but this was just something about the last decade or so. The point I want to make is that we are aware of this, and people are trying to fix this. Okay, and so if you look at a data set over here in centrum semiovale, coronal section over here, this is what DTI would provide you. And then given the same data with another model, in this case a spherical deconvolution approach, you can get a lot more rich information about the different orientations that are captured within this voxel. How prevalent is this issue? Again, it's almost all over the brain, right? And this is at least what the data predicts. Okay, so in my view, every voxel contains these crossing fibers, even in the corpus callosum. And think of the example that I showed about Russ Poldrack's brain, the heterogeneity there. So, you know, I wouldn't be amazed that at least at the 2x2x2 voxel resolution, you can actually capture all these different peaks. Okay, so and obviously this has an effect on tractography. If you're looking at whole brain tractography over here, this is just showing you the difference. And if you look at a specific region over here, mid-coronally, part of the corpus callosum, you can clearly see these U-shaped pathways. And if we then use the same data, same seed region, but then a different model, you'll get something like this. So this is a spherical deconvolution approach, for instance, where you can clearly see these lateral projections also going, you know, over here and over here. You can even see the omega shape over here as well. So at least I can say it's different. And the nice thing about these spherical deconvolution approaches is that you can actually use them with clinical data as well, so you don't need to really push the limits of your scanner there, but you can clearly see the differences for the, you know, the two different techniques over here as well. And finally, I would like to say something about TBSS. Okay, so it's a voxel-wise analysis. It's by far one of the most popular approaches to look at this voxel-wise analysis. It works a bit like this. So you've got, let's say, your FA maps of your healthy controls. You've got your FA maps of your pathology or another group you want to compare. Then use the right button, and boom, you get your answer. Okay, so that's one of the reasons why it's so popular. It's very user-friendly. Kidding aside, how it really works is you create a common template from which you then create a skeleton. And this skeleton is then basically back projected to each subject. And then you get your statistical inferences. But just like tractography, this voxel-wise analysis is not perfect either, right? And there's many issues there that is described in this paper. I'll just touch upon a few. First of all, it can be sometimes confusing for people. You know, they use this term tract skeleton. Well, I would prefer to keep FA skeleton as they started off with in their paper, but because if you just compare a tract skeleton and an FA skeleton, it's not the same. You can actually overlay them, and it's not really, you know, you can actually expect it to be different because the FA map does not contain any orientation information, right? So in this case, the orientation information is neglected. Another aspect is related to the actual projection strategy. So if you, in this case, look at, let's say, a healthy control and do the back projection to each data set, then you'll get this one. So this is finding the locally maximal FA value. But if you have pathology, then obviously your projection might actually terminate prematurely here because of the design of finding the local maximal FA value. Another aspect is in terms of the interpretation. So if you look at this area, for instance, you know, is this the corpus callosum or part of the cortical spinal tract? Right? It's difficult to say. So different anatomical structures may be overlapping on each other when doing the back projection. But interestingly, obviously, because it's not tract-based, why do we actually call it TBSS? Well, who was the last author of the paper? That was Timothy Behrens, right? Who was the first author of the paper? That was Steve Smith. TBSS, Timothy Behrens, Steve Smith. Anyways, at least they've got a sense of humor. And with this, I would like to end my presentation and thank you for your attention.